Ever found yourself looking at a really complex problem, feeling like you needed some kind of, I don't know, secret decoder ring just to get started? What if we told you there's actually a shortcut? A really powerful idea that underlies everything from, say, rocket science to predicting the stock market. Today, we're taking a deep dive into exactly that kind of concept: limits in calculus. Specifically, we're digging into the properties of limits and techniques of limit computation. Our mission, really, is to demystify these mathematical tools. We want to show you how you can compute limits, sometimes with surprising ease, and reveal the elegant logic behind calculations that might look pretty complex at first glance. This deep dive is all about getting those aha moments so you understand not just what a limit is, but how we figure it out, and crucially, why these methods are so important. We've basically boiled down the key ideas from a pretty detailed lecture on this, making it accessible and hopefully really engaging for you. All right, let's start right at the beginning, and let's unpack this core idea. When we talk about a limit in calculus, what exactly are we, talking about?
It's a great question, and it's really about anticipation, isn't it? About the trend. It's not always about what a function is right at a specific point. Instead, it's about what its output, its y value is approaching as the input, the x value, gets incredibly infinitesimally close to some specific number. Let's just call that number a.
Okay, so getting closer and closer, like zooming in.
Exactly. Think of zooming in on a map. You keep getting nearer and nearer to a spot, but maybe you never actually land exactly on it. Graphically, you can picture tracing along a function's curve. The limit at a is the y value you'd expect to hit if you approached a from both sides, from the left and from the right. If both approaches lead you to the exact same y value, well, then the limit exists. It's all about that convergence, that agreement for both directions. It tells us the function is behaving predictably near that point.
That map analogy helps a lot. So a limit is about where a function is headed. Let's start super simple. What about a constant function like fx equals c? Just a flat horizontal line. If you pick any point A on the x-axis and approach it, what's the y value doing? Or rather, what's it approaching?
Right, well, the beauty of a constant function is it doesn't do anything. It's just c, always. So whether you're coming at xa from the left or from the right, or even if you're right at a, the y value is just c. It never changes.
So the limit is just the constant value itself.
Exactly. The limit of any constant c as x approaches any number a you like is simply c. It's always approaching its own value because it is its own value everywhere. It seems almost trivial, but it's a fundamental building block. We write it, formally as lim as x approaches a if c is c.
Okay, got it. Now, what about something just a tiny bit more dynamic, like the identity function, fx equals x, that diagonal line through the origin? If x is approaching some number a, what's the y value doing there?
Well, this is another one that feels pretty intuitive, but it's really important. For a simple, smooth function like y equal x, as x gets closer and closer to a, the y value, well, it's just equal to x, right? So the y value must also be getting closer and closer to a. If x is approaching, say, 5, then y is approaching 5.
So the limit is just a again.
Precisely. The limit of x as x approaches a is simply a. It sounds obvious, maybe, but this result is incredibly useful. It's another foundational piece we use to build up understanding of more complex limits.
Right, so for these basic functions, limits seem pretty straightforward. But what happens when we start combining functions? Adding them, subtracting, multiplying, dividing. Are there rules for that, like algebraic rules?
Oh, absolutely. There's a set of really elegant, powerful properties for limits. But, and this is really important, there's a condition. These rules only work if the individual limits of the functions involved, let's call them fx and gx, actually exist as x approaches the exact same value a.
Okay, so both parts need to be behaving nicely on their own first.
Exactly. If one limit doesn't exist, or if they're approaching different points, then you can't just apply these rules blindly. It's like needing solid ground before you build something on top.
Makes sense. So let's talk addition and subtraction. If we've got fx plus gx inside a limit, can we just split that up? Find the limit of fx and the limit of gx separately and add them.
You got it. That's the sum rule.
Mm-hmm.
It's incredibly helpful because it lets us break down complicated expressions. The limit of fx plus gx is just limit of fsx plus limit of gx. And the same exact logic applies to subtraction. The limit of the difference is the difference of the limits. It's what lets us handle polynomials with lots of terms.
Okay, cool. And multiplication, if they're multiplied inside, like fx.
Yep, same idea. You could separate them. The limit of fx gx is limit of fx, limit of gx. This is super useful, especially with polynomials where you have constants times variables or variables times other variables. You can often pull constants right out of the limit calculation.
All right, and division.fx gx. Can I just divide the limits?
Yes, but, and this is a huge but, with a critical condition. The limit of the function in the denominator, gx, cannot be 0.
Ah, the classic don't divide by 0 rule.
Exactly. If that denominator limit is 0, it's a red flag. It signals a potential problem, maybe an asymptote, maybe something else, and we need different techniques, which we'll definitely get into. But if the limit of the denominator isn't 0, then yes, the limit of the quotient fx, gsx, is simply limit of fx, limit of gx. Always check that denominator first.
Okay, last property for now, and this one sounds like it could really simplify things. Taking the limit of a function raised to a power, like fxn.
Yes. This one is, I think, particularly neat. It says you can absolutely find the limit of the function first and then raise that result to the power n. So the limit of fxn is the same as limit of fxn. It lets you move the exponent effectively outside the limit operation.
Oh, that's useful.
It really is. And this applies to roots too, right? Because a square root is just a power of 1/2, a cube root is a power of 1/3, and so on. So the limit of the square root of fx is just the square root of the limit of fx. It makes dealing with powers and roots inside limits much, much easier.
So we've got these properties: addition, subtraction, multiplication, powers. If we put them all together, what does that mean for finding limits of polynomials? You mentioned polynomials earlier. Is there a big shortcut?
There absolutely is, and it comes directly from applying all those properties. If you think about a polynomial, it's just sums and differences of terms involving constants times x raised to whole number powers. We know how to handle sums, differences, constants, multiplication, and powers with limits. When you apply all those rules to any polynomial, px, something amazing happens. As x approaches some number a, the limit is simply pa. You just plug the number a directly into the polynomial.
Wait, really? Just plug it in? That seems almost too easy after building up all those rules.
Yeah, it does, doesn't it? But it works because polynomials are, mathematically speaking, incredibly well behaved. They're continuous everywhere. Their graphs are smooth curves with no jumps, no holes, no vertical asymptotes. So the value the function is approaching as x gets close to a talk is exactly the same as a function's value at a
Can
key.
we see an example? Show us how the properties lead to that shortcut. Maybe lim by 3, 2x plus 7 as x approaches 2.
Perfect example.
Yep.
Okay, if we did it the long way using the properties, first split by subtraction and addition, lim by 3 lim 2x plus lim 7, then apply the power rule to by 3 and the constant multiple rule to 2x, lim by 3 lim 2 lim x plus lim 7. Now use the basic limits. Lim x is x2 is 2, lim 2 is 2, lim 7 is 7, so we get 2, 3, 2 plus 7. That's 8, 4 plus 7, which equals 11.
Okay, that's the long way and the shortcut.
The shortcut. Just plug x2 directly into by 3, 2x plus 7, you get 2, 3, 2 plus 7 plus 8, 4 plus 7 equals 11.
Identical. Wow.
Exactly. It's a massive time saver.
That really is an aha moment. So for lots of nice functions, finding the limit is just evaluating the function. Why is that predictability so important, practically speaking?
Oh, it's crucial. Think about engineering, physics, economics. Anywhere, you're modeling how things change. If you're modeling the path of the spacecraft or the stress on a bridge using a polynomial, you need to know that the calculated value accurately reflects what the system is approaching at a critical point. This niceness, this continuity, this direct substitution rule, it's what makes those calculations reliable. It simplifies things immensely and builds the foundation for more complex calculus, like figuring out rates of change. It's not just a trick. It's fundamental to how we model the real world predictably.
Okay, but things aren't always that nice and simple, right? What happens if using that plug-in rule gives you something problematic, like 0, 0, 0, 0 divided by 0? What does that mean? Does the limit just not exist?
That's a fantastic question, and it's where things get really interesting. Getting 0, 0 is what we call an indeterminate form. Critically, it does not automatically mean the limit doesn't exist. Think of it more like the math is saying, I need more information, or try a different approach. It often indicates there's some kind of cancellation possible, or maybe a hole in the graph right at that point that we need to account for algebraically. It means more work is needed, not that it's impossible. So the main strategy when you hit 0, 0 with rational functions, that's polynomials divided by polynomials, is usually algebra. Specifically, if plugging in xa gives you 0, 0, it's a very strong hint that XA is hiding as a factor in both the numerator and the denominator.
Ah, so you factor both top and bottom.
Exactly. You factor both, find that common XA factor, and then this is the key. You cancel it out. After canceling, you try plugging A into the simplified expression again. Usually the 0, 0 problem disappears.
Okay, factoring and canceling. Can we see that in action? Give us an example.
Sure. Let's take lim by 2, 4 by 2 as x approaches 2. If you plug in 2, you get 22, 4, 2, 2, which is 4, 4, 0, yep, 0, 0, our signal.
Right, factor time.
Factor time. The numerator, by 2, 4, is a difference of squares, by 2x plus 2. So the expression becomes by 2x plus 2 by 2. Now here's the crucial insight. Because x is approaching 2, it's getting really close, but it's never exactly equal to 2.
So by 2 isn't actually 0.
Precisely. Since by 2 isn't 0 in the neighborhood we care about, we are perfectly allowed to cancel the by 2 factor from the top and bottom. What are we left with? Just x plus 2.
And now we can plug in 2.
Now we plug x goes 2 into the simplified x plus 2, and we get 2 plus 2 equals 4. So the limit is 4.
That's clever. It feels a bit like magic, just canceling that term away. Why does that fix the 0, 0 issue and give us the real limit?
It's because limits care about the journey, not just the destination point itself, especially if that point is problematic. The x2 factor was causing the 0, 0 issue, indicating what's called a removable discontinuity, basically a tiny hole in the graph at x22. By canceling x2, we're essentially finding an algebraically equivalent function that doesn't have that specific hole but matches the original function everywhere else. We've algebraically patched the hole, revealing the y value the function was heading towards all along. We found the intended destination, even if the exact spot had a pothole. But what happens if you factor, you simplify as much as you possibly can, and you still end up with a 0 in the denominator when you plug in xa. But this time the numerator isn't 0. So you get something like, say, 50 or negative 20.
Ah, so not 0, 0 anymore, but still dividing by 0. What does that mean?
That usually signals something different, a vertical asymptote. The function is likely shooting off towards positive or negative infinity near that point. It's not a simple hole we can patch. In these cases, where you get non-zero number 0, the limit might be plus infinity of infinity, or might not exist at all if it goes different ways on either side. And to figure that out, we need a different tool, the sign analysis test.
Okay, sign analysis test. How does that work? How do we use it to figure out the behavior near an asymptote?
It's a way to check the function's direction just to the left and just to the right of the problem point A. You pick a test value that's really close to A but slightly less than it, like a 0.001. Plug this into your simplified function and just note the sign, positive or negative of the result. Then you do the same thing with the test value really close to A but slightly greater than it, like a plus 0.001. Plug it in, note the sign.
And what do the signs tell us? Positive on both sides, negative on both, or maybe one of each?
Right. Here's the interpretation. If both sides give you a positive result, meaning the function's going way up towards plus infinity from both left and right, then the limit exists and is plus infinity. If both sides give you a negative result, meaning it's diving down towards infinity from both sides, the limit exists and is infinity. But if one side gives a positive result, plus infinity, and the other side gives a negative result in infinity, then the function is heading in opposite directions. In this case, the limit does not exist, D&E. It doesn't converge.
Got it. So matching infinities mean the limit is infinity. Opposing infinities mean D and E. Can we see an example of this sign test?
Sure. Let's look at lim x plus 2 by 5 and 5 as x approaches 5, direct substitution, 5 plus 2, 5 to 5 equals 70. Okay, that's our non-zero, 0 situation. It smells like an asymptote. No factoring helps here.
Time for sign analysis.
Sign analysis it is. Let's test just to the right of 5. Pick x, what was 5.001. Plug it in. 5.001 plus 2. 5.001. 5 equals 7.001. A call that's equal to 2.01. That's positive, divided by positive, so the result is positive. The function goes to plus infinity from the right. Now let's test just to left of 5. Pick x was 4.999. Plug it in. 4.999 plus 2. 4.9999 negative 0.001. That's positive divided by negative, so the result is negative. The function goes to negative infinity from the left.
Ah, so positive on the right, negative on the left, they don't match.
Exactly. Since the left-hand behavior, 9 infinity, doesn't match the right-hand behavior, plus infinity, the overall limit as x approaches 5 does not exist, D&E.
Okay, so we have factoring for some 0, 0 cases, sign analysis for non-zero, 0, 0. But what if we get 0, 0, 0? And simple factoring doesn't seem to work, especially when square roots are involved. That seems trickier.
You're right. Square roots, or radicals in general, can make factoring less obvious. If you hit 0, 0 with a radical expression and factoring isn't jumping out at you, there's another powerful algebraic technique, multiplying by the conjugate.
The conjugate, that sounds familiar. How does it work again?
The conjugate is formed by just flipping the sign between two terms. So the conjugate of AB is A plus B and vice versa. If you have a term like squared EX3, its conjugate is squared EX plus 3. The trick is to multiply both the numerator and the denominator of your fraction by the conjugate of the part containing the radical that's causing the 0, 0 issue. This often cleverly eliminates the radical from that part thanks to the difference of squares pattern, AB, A plus B, E2, B2, and frequently reveals a common factor you can then cancel. It's a way to sort of rationalize the expression.
Okay, multiplying top and bottom by the conjugate. Let's see it work. How about lim squared EX1 by 1 as x approaches 1?
Perfect example. Plug in 1, squared EX 1, 1, 1, 1, 1, 0, 0, 0, 0. Okay, indeterminate. The radical is in the numerator, squared EX1. The conjugate is squared dx plus 1. So we multiply top and bottom by squared dx plus 1, squared dx plus 1, squared dx plus 1. Now multiply out the numerators using the difference of squares. Squared dx plus 1 radicals are 212, both by 1. By 1. That looks useful. It sure does. So our expression is now by 1, squared tx plus 1. Look at that. We have by 1 on the top and by 1 on the bottom. Since x is only approaching 1, x1 isn't 0, so we can cancel them.
Leaving 1 squared tx plus 1.
Exactly. And now we can safely plug in x squared t1 plus 1, x squared 1 plus 1 equals 12. The limit is 12.
That conjugate trick is pretty neat. It cleaned that right up.
Yeah.
Any tips or pitfalls when using conjugates? Like, should we multiply everything out?
Good question. Generally, when you multiply by the conjugate, only multiply out the part you're trying to fix, the conjugate pair. Leave the other part factored. In our example, we multiplied out the x1 in the numerator, but we left the x1, x plus 1 in the denominator alone. Why? Because our goal is almost always to find that common factor, like x1, to cancel. If you multiply everything out immediately, you might hide the very factor you're looking for. Keep the other part factored initially.
Okay, we've handled polynomials and rational functions pretty well. But what about those functions that are defined differently in different pieces? You know, piecewise functions. How do we find limits when the rule itself changes?
Piecewise functions. They definitely require a bit more care. Because the function's definition can literally switch at certain breakpoints, we absolutely cannot just plug in the number blindly if it's one of those points. We have to consider the approach from both sides separately, using the correct piece of the function for each approach. This is where the idea of one-sided limits becomes essential.
One-sided limits. So the limit from the left and the limit from the right. How do we keep track of which function piece to use for which side?
A really helpful visual is the number line approach. Just draw a quick number line, mark the points where the function definition changes, the breakpoints. This makes it super clear which function rule applies to the numbers just to the left of a breakpoint, we denote that as xa, and which rule applies to numbers just to the right, xa plus.
Okay, so use the number line to pick the right rule for each side. Then what?
Then you calculate the limit from the left using its rule, and the limit from the right using its rule. And here's a fundamental rule. The overall limit as x approaches exists if and only if the left-hand limit is equal to the right-hand limit. If they approach different values, the limit at that breakpoint does not exist, DNE. They have to agree.
That number line idea sounds practical. Let's try an example. Say we have a function, fx, defined like this.
Yeah.
fx, 1x plus 2, if x by 2, 5, if next 2, x equals 3, if x equals 3, x plus 13. Looks like breakpoints at x minus 2 and x equals 3. Let's find the limit as x approaches 3.
Okay, breakpoint x3. First, the limit from the left, x minus 3. Which rule applies for x slightly less than 3?
That'll be the middle one by 2, 5.
Right, so we plug 3 into by 2, 5. That gives 3, 2, 5 equals 9, 5 is 4. The left-hand limit is 4. Now the limit from the right, x minus 3 plus. Which rule for x slightly greater than 3?
The last one, square root x plus 13.
Correct. Plug 3 into square root x plus 13. We get square root of 3 plus 13. Square root of 16 equals 4. The right-hand limit is also 4.
Hey, they match. Both are 4.
They do. Since the left-hand limit equals the right-hand limit, the overall limit of fx as x approaches 3 exists and is equal to 4. The function comes together nicely at x3.
Okay, clear. Now for the other breakpoint, x equals 2, that first piece, 1x plus 2, looks like it might cause trouble near megas 2.
Good eye. Let's check x equals negative 2. First, the limit from the right, x minus 2 plus. Which rule applies for x slightly greater than megas 2?
Still the middle one by 2, 5.
Right. Plug negative 2 into by 2, 5. We get negative 2, 5 equals 4, 5 equals 1, negative 1. Now the limit from the left, x minus a 2. Which rule for x slightly less than negative 2?
That's the first one, 1x plus 2.
Okay. If we try to plug -2 into 1x plus 2, we get 1, 2 plus 2 equals 10.
Ah, the non-zero-zero situation again, asymptote.
Looks like it. So direct substitution fails, and we need sign analysis for this left-hand limit. Let's pick a test value just to the left of -2, say x equals -2.00. Plug it into 1x plus 2.
Right.
1 -2.001 plus 2. That's positive divided by negative, so it's negative. The function goes to negative infinity from the left.
Okay, so the left limit is negative infinity, but the right limit was -1.
Exactly. They absolutely do not match. One is finite, the other is infinite and negative. Therefore, the overall limit of f's as x approaches mex 2 does not exist, DNE. This shows why checking both sides is so critical for piecewise functions.
All right, let's switch gears a bit and bring in some trigonometry. What about limits involving functions like sine and cosine? Are they nice like polynomials? Can we just plug in the number?
That's a great question, and it comes back to that idea of continuity we talked about. Sine and cosine functions are beautifully continuous everywhere. You can draw their weighty graphs forever without lifting your pencil. No breaks, no holes, no asymptotes.
So direct substitution works for them too.
It absolutely does. For sine and cosine, the limit of sin x as x approaches a is simply sin a. The limit of cosine x as x approaches a is simply cosine. Just plug it in. For basic sine and cosine limits, it's that straightforward.
Okay, that's good news. But what about tangent, tan x? Does that work the same way?
Tangent is a bit different. Remember that tan x equals sec cos x. Well, sine and cosine are continuous everywhere. Tangent runs into trouble whenever its denominator, cos x, equals 0.
Right, which happens at pi 2, 3p2, etc.
Exactly. So the limit of tan x as x approaches a is tan n as long as cos is not 0. If cos is 0, meaning is one of those odd multiples of pi 2, then you have a vertical asymptote. You'd get a non-zero situation, and you'd need to use sign analysis, just like with rational functions, to see if the limit is plus infinity, and infinity, or d and e.
Okay, so tangent needs a little extra caution. What if we have compositions? Like a function inside a cosine, say lim cos fx.
That brings us to a very handy rule. The composition rule for limits, specifically when the outer function is continuous like cosine is. You can essentially push the limit operation inside the continuous outer function. So lim cos as x approaches a is the same as cos lim f as x approaches a.
Oh, so find the limit of the inside part first, then take the cosine and the result.
Precisely. You evaluate the limit of the inner function fx, get a value, let's say L, and then your answer is just cos L. It simplifies the process nicely.
Can we see a quick example of that?
Sure. Let's find lim cos by 2, 1, a1 as x approaches 1. First, we deal with the inside limit. Lim by 2, 1 as x1 as x1. We saw this one earlier. It's 0, 0. We factor by 2, 1 to x1, x plus 1, cancel the x1, leaving lim x plus 1 is x1. Plugging in 1 gives 1 plus 1 is 2.
Okay, so the inside limit is 2.
Right. Now we just apply the outer function, cosine, to that result. The final answer is simply cos 2.
Now, here's where things get really interesting, I think. There are some famous trig limits, like lim sin xx as x goes to 0. Plugging in gives 0, 0, 0. How on earth do we figure that one out? Factoring doesn't seem to help here.
You're right. Direct substitution and simple factoring fail us there. This is where we need a more sophisticated tool, a really clever idea called the squeeze theorem. Some people call it the sandwich theorem.
Squeeze theorem. Okay, what's the idea?
Imagine you have a function that's maybe behaving weirdly, oscillating or something, like sin xx near 0. The squeeze theorem says, if you can find two other simpler functions that you know the limits of, and you can prove that your tricky function is always squeezed or sandwiched between these two simpler functions near the point A, and if those two outer sandwiching functions both approach the same exact limit L as x approaches a,
And the function in the middle.
has no choice. It must also approach that same limit L. It gets squeezed towards the same value. It's a really elegant way to find limits of functions that are otherwise hard to pin down.
That's a cool visual.
Yeah.
Sandwiching the function. How does that work for sin? How do we
Okay.
prove it goes to 1 using this squeeze idea? Seems like magic.
It feels a bit like magic, but it's solid geometry and logic. We can use a unit circle. Imagine a unit circle and a small positive angle x in radians. We compare the areas of 3 shapes. 1, a small triangle inside the sector with height sin x and base 1, area equals 12 sin x. 2, the circular sector itself with angle x, area equal 12 r2x, it's r1. 3, a larger triangle outside the sector formed by the tangent line with height 10x and base 1, area equal to sin x.
Okay, 3 areas, and the sector is clearly between the 2 triangles in size.
Right, so 12 sin x, 12x, 12 tenths multiplied by 2 sin x. Now let's divide everything by sin x, which is positive for small positive x. 1x sin xx, we know tan x sin x simplifies to 1 cos x. So 1x sin x, we want sin x. So let's take the reciprocal of everything. Remember to flip the inequalities. 1 sin x, x cos, or written more nicely, cos sin x1.
Well, we squeezed it. It's between cos x and 1.
Exactly. Now apply the squeeze theorem as x approaches 0. What's the limit of cos x is x0? It's cos 0, which is 1. What's the limit of 1 is x0? It's just 1. Since stick x is squeezed between two functions that both approach 1, the squeeze theorem guarantees that lim sin x as x approaches 0 must also be 1. And this works for x approaching 0 from the negative side too.
That is genuinely elegant. Wow. So if this lim sin x whole 1 is a big deal, are there other special trig limits like this we should know? Kind of like magic identities for limits?
Yes, there are three essential ones that are incredibly useful, especially for resolving zero-zero forms in trig limits. It's highly recommended to memorize these. 1 lim sin xx, that's 1, as x minus 0, the one we just proved. Sine matches its angle near 0. 2 lim 1 cos x, x 0, 0. This one comes from multiplying by the conjugate 1 plus cos x and using identities. The key takeaway is this 1 cosine form over x goes to 0. 3 cos lim tan x equals 1 as x minus 0. This one follows easily from the first one since tan x, sin x, 1 cos x, and both factors go to 1 as x minus 0.
Okay, so sin x minus 1, tan x minus 1, but 1 cos x minus 0.
Got it. Those seem like essential tools for the trig limit toolbox. So we have these three magic trig limits. But what if the problem we're given doesn't look exactly like sin x? What if it's, say, sin 2xx or sin 5x, sin 6x? How do we use our special limits then?
That's where a technique called angle matching comes in. It's all about algebraic manipulation. The goal is to make the argument of the sine or tangent function exactly match the term in the denominator. If you have sin 2x upstairs, you ideally want 2x downstairs to use the sin minus 1 rule. We achieve this by multiplying the expression by a clever form of 1 like 22, 55, xx, whatever is needed to make the angle match the denominator, or vice versa. It rearranges things into the form we need.
Okay, multiplying by 1 in disguise. Let's see some examples. How about that lim sin 2xx as x approaches 0? Right, we have sin 2x on top, but only x on the bottom. We need 2x on the bottom. So multiply by 22. Lim sin 2x, x 22. Now rearrange lim 2 sin 2x is x0. We can pull the constant 2 out front. 2 lim sin 2x is x0. Now look at the limit part. Lim sin 2x as x0, clearly 2x also goes to 0. So this fits the form lim sin u as u0, where u equals 2x.
Then that limit is 1.
Exactly. So the whole thing becomes 2, 1 equals 2. How about the other one you mentioned? Lim pi x sin 6 as x approaches 0.
Yeah, that looks trickier. 0, 0 again.
Yep. Here, we need an x term in the denominator for both the sin 5x and the sin 6x. A neat trick is to divide both the numerator and the denominator by x lim sin 5xx in 6x as x0. This is like multiplying by 1x, 1x.
Okay, now we have terms that look closer to the special limit.
Almost. Now we apply angle matching to the top and bottom separately. Top sin 5xx, we need 5x downstairs, so multiply by 55, 5 sin 5x. Bottom sin 6x, we need 6x downstairs, so multiply by 66, 6 and 6x. Putting it back together, lim 5, sin 5 by 5x, sin 6 by 6x as x0. As x0, both sin 5 by 5x and sin 6, 6x approach 1.
So we're left with 5, 1, 6, 1, which is 56. Clever.
Isn't it? Careful algebraic steps make it work out nicely.
What if the angle isn't just a multiple of x, like, say, lim sin by 2x as x approaches 0?
Good question. The angle is by 2. So ideally, we want by 2 in the denominator. We only have x. We need another factor of x downstairs. Let's multiply by xx, lim sin by 2xx. Rearrange the lim x n by 2x, which is lim x n by 2 is x0. Now we can split this using the product rule for limits. Lim x is x0, lim sin by 2 as x0.
Okay, the first part, lim x is x0, is just 0.
Right. And the second part, lim sin by 2 as x0 by 2 also goes to 0. So this is our sin u form again, where u fills by 2. That limit is 1.
So the whole thing is 0, 1, which is 0.
Exactly. 0, 1 is 0. Angle matching works even with more complex angles.
Okay, angle matching is powerful. But sometimes maybe the expression looks really different and angle matching alone isn't enough. Can trigonometric identities help us transform the problem before we try to match angles?
Absolutely.
Yeah.
Knowing your trig identities is crucial here. Sometimes applying an identity is the first step needed to simplify the expression into a form where you can then use the special limits or angle matching. Identities like the Pythagorean identities, sin 2x proves 2x equals 1, double angle formulas, sum difference formulas, cofunction identities, they can all be potential keys to unlock a difficult limit.
Can we see an example where an identity is the main trick?
Sure. Let's try lim tan to t 1 cal 2t as p throws t approaches. Plug in 0 potangent 0, 1 cos to 0, tan to t 112 0 0 0. Okay, indeterminate. Do we see any identities? That denominator, 1 cos 2t, should ring a bell.
Pythagorean identity, 1 cos 2t is as c sub p.
Exactly. Let's substitute that in. Lim tan 2t cz dO. We can rewrite this as lim tan t2 as tdo. Let's simplify the inside part. Tan t tt is ct cos c. The sin t cancels, leaving 1 cos t.
Oh, nice simplification.
So the limit becomes lim 1 cos t2 as td0. Now, can we plug in T0?
Mm-hmm.
Cos 0 is 1, which is not 0. So yes,
Mm.
1 cos 2, 2 equals 1, 12 equals 12 equals 1. The limit is 1. The identity was key. Here's another one. Lim sin x cos p2x as x approaches 0. Plug in 0.0 cos pi c 0 cos p o 0, 0, 0, both 0. Indeterminate. Any identities jump out. Cos pi 2x.
That's a cofunction identity. Cos pi 2x.
Bingo. Substitute it in.
Mm.
Lim sin x as x0. Since x is only approaching 0, sin x isn't 0, so we can cancel sin x and x.
Leaving just lim 1 as x0.
Which is, of course, 1. Again, the identity made it almost trivial.
Okay, it seems like for more complex problems, we might need to use several of these techniques together, right? Maybe split things up, use an identity, then do angle matching.
Absolutely. That's very common. Many limits require a sequence of steps, combining algebraic manipulation like splitting fractions, trigonometric identities, and angle matching, all geared by the goal of getting to those 3 special limit forms. It's like solving a puzzle.
Let's tackle a tricky one then. How about lim 2 cos 3x cos 4x x as x approaches 0? Plugging in gives 2, 1, 1, 0, 0, 0, 0. Looks like a job for combined strategies.
Indeed. 0, 0. Our goal should be to somehow create terms that look like 1 cos u, since we know that goes to 0. Notice the 2 in the numerator, we can cleverly rewrite that as 1 plus 1. So lim 1 cos 3x plus 1 cos 4x as x0.
Now we have 2 1 cos forms.
Exactly. Now, since they share the denominator x, we can split the fraction and limit. Lim 1 cos 3x as x0 plus lim 1 cos 4x, x is x0. Now we apply angle matching to each part. First part. 1 cos 3x, we need 3x downstairs, multiply by 33, lim 3, 1 cos 3x is x0. Second part, 1 cos 4x, we need 4x downstairs, multiply by 44, lim 4, 1 cos 4x, and x0.
Okay, and we know lim 1 cos 0 is 0.
Right, so the first term becomes 3, 0, 0. The second term becomes 4, 0 equals 0. Adding them together, 0 plus 0 equals 0. The limit is 0. Required splitting and angle matching.
That's great. How about one more, maybe involving division? Lim by 2 3c's in x approaches 0.
Okay. Plug in 0, 0, 0, 2, 0, 0 equals 0, 0, 0, 0. Indeterminate again. We could split the fraction here too because of the common denominator x, lim by 2x, 3 sin x as x0.
And simplify by 2x to just x.
Right. So we have lim by 3 sin x as x0. Now split the limit using the difference rule. Lim x is x0, lim 3 sin x is x0. Evaluate each piece. Lim x is x0 is just 0 point. Lim 3 sin x is x0. Pull the 3 out. Lim sin x is 1, so this is 3, 1, Easter 3.
So the answer is 0, 3, which is 0, 3.
Precisely. 0, 3 equals Naser 3. Another example combining algebraic splitting with our special trig limits.
We've successfully found limits for so many functions, even complicated ones, but you mentioned earlier that sometimes limits just don't exist. What about functions that are just too chaotic near a point?
That's a crucial point to remember. Not all functions settle down nicely. Some oscillate too wildly, or they approach different values from the left and right, like we saw with some piecewise functions or asymptotes. If a function doesn't converge towards one specific y value, then the limit does not exist.
Can you give us an example of a function that oscillates so much its limit doesn't exist?
The classic example is lim sin 1x, as x approaches 0. Think about what happens to 1x as x gets really tiny, approaching 0. 1x shoots off towards positive or negative infinity. So sin 1x is basically taking the sign of enormous and rapidly changing numbers. This causes the sine function to oscillate infinitely fast between -1 and 1 as x gets closer and closer to 0. If you tried to graph it near the y-axis, it would just look like a solid band between y1 and y1. It never settles on a single value.
So no convergence means no limit. DNE.
Exactly. For lim sin 1x as x0, the limit does not exist.
But didn't you mention, what if we put an x in front of that? Like lim x sin 1x as x approaches 0. Does that x manage to calm it down?
Yes. This is where it gets really fascinating. It brings back our friend the squeeze theorem. That multiplying x term, even though it's approaching 0 itself, acts like a damper or a squisher on the wild oscillations of sin 1x.
How does the squeeze theorem work here? We still have that crazy sin 1x part.
We start with what we know for sure. Sin 1x, no matter how crazy 1x gets, is always trapped between 1 and 1. So minus 1x, 1x equals 1. Now, I want to get x sin 1x in the middle. Let's multiply all parts of the inequality by x. We need to be a bit careful if x is negative. But using absolute values handles it neatly. We can say for sure that x sin 1x must be between minus x and x. So minus x sin 1x. This holds whether x is positive or negative near 0.
Okay, so we've squeezed x sin 1x between minus x and x.
Exactly. Now, what happens to the outer functions as x approaches 0 point limit x as x0 is limit x as x0 is also 0.
They both go to 0.
They both go to 0. So by the squeeze theorem, the function trapped in the middle, x sin 1x, must also approach 0 as x approaches 0.
Wow, so the x term multiplying it actually tames the oscillation and forces the limit to be zero.
Precisely. It's a beautiful demonstration of how multiplying by something going to zero can damp down even infinite oscillations and create a well-defined limit.
Hashtag Outerette. Wow, okay, that was quite the journey through the world of limits. We've really taken a deep dive today, uncovering some incredibly powerful mathematical ideas. We looked at the basic properties, how limits interact with addition, multiplication, powers. We saw the fantastic shortcut for continuous functions like polynomials, sine and cosine, just plug it in. And we tackled the tricky parts too, that 0, 0 form, using factoring, conjugates, even sign analysis for asymptotes. We navigated piecewise functions using one-sided limits and unlocked trig limits with those special identities and the really elegant squeeze theorem. You should now have a pretty solid toolkit for evaluating limits.
Absolutely. If we boil it down, the key takeaways are probably, first, always try direct substitution. For nice functions, it's often all you need. Second, remember 0, 0 is indeterminate, not necessarily D&E. It usually means do more algebra factor, use conjugates to simplify. Third, if you get non-zero, zero, think vertical asymptote and use the sign analysis test to check behavior from both sides. Fourth, for piecewise functions at breakpoints, left-hand limit must equal right-hand limit for the overall limit to exist. And fifth, those three special trig limits involving sin x, 1 cos xx, and tan x as x0 are crucial. Know them and practice using angle matching and identities to get your problem into one of those forms. Oh, don't forget the squeeze theorem for those tricky oscillating cases.
That's a great summary. So, thinking beyond the math class, what's a final thought for you, our listeners, to mull over? Well, consider how these techniques, focusing on what a function approaches, really set the stage for the next big idea in calculus: the derivative. If a limit tells us where something is heading, how might that help us define an instantaneous rate of change? Like the exact speed of your car right now, not just its average speed. Or how fast a population is growing at this very moment. What else in your world, maybe in economics, technology, biology, even social trends, could be better understood not just by looking at where it is, but by analyzing where it seems to be approaching? Something to think about. We hope this deep dive gave you some valuable insights and tools. Until next time, keep exploring.